Welcome to The Explainer. Today, we're going to dive into a really fascinating paradox in AI. How can a model actually be too smart? We're going to look at a technique that basically teaches models to learn the big picture instead of just, memorizing all the answers for the test.
Yeah, it's a weird question, right? I mean, you spend all this time and energy training a model. You're pushing it to learn every single little detail in your data. But what happens when it learns too well? Like when it just memorizes the answers to the test instead of actually understanding the subject. That's the exact problem we're going to unpack today. So this whole problem has a name. It's called overfitting. And trust me, it's a massive headache in the world of machine learning. You can kind of think of it like a model that's a super specialized expert. It knows everything about the stuff it's already seen, but then it's totally lost when it sees something new. Okay, so this is what that looks like in the real world. You look at the training data and, hey, the model's a genius, 99% accuracy. It looks like a huge success. But then you show it some new data, stuff it's never seen before, and its performance just tanks. We're talking 55%. What happened? Well, it didn't actually learn the real pattern. It just memorized all the little quirks and noise in the training set. So how do we fix this mess? How do we get our model to actually generalize what it's learned instead of just memorizing? Well, there's a really clever solution, and it all comes down to putting a penalty on being too complex. And this technique is called regularization. So here's the big idea. It works by adding this complexity penalty directly to the model's loss function. Now, if you're not familiar, the loss function is just a score that tells the model how wrong its predictions are. The lower the score, the better. So by adding this penalty, we're basically changing the rules of the game for what it means to get a good score. Honestly, the best way to wrap your head around this is to think of it as a complexity tax. We're literally telling the model, look, it's not enough to just be right on the training data. You also have to be simple. The more complicated you get, the more tax you're going to have to pay. And this forces a trade-off, right? The model might give up a tiny bit of its perfect score on the training data, but in exchange, it becomes way simpler. And because of that, much, much better at handling new stuff out in the wild. Okay, so how does this tax actually work in practice? Let's pop the hood and look at the most common type, which is called L2 regularization. And don't worry, the math here is way more straightforward than it sounds. All right, so normally, before we do any of this, a model has just one goal during training: minimize its original loss. And that's just a fancy way of saying minimize the error, how far off its predictions are from the right answers. The whole point of training is to get that number as close to zero as you possibly can. But with regularization, we shake things up. We change the equation. We add a brand new piece, the regularization term. So now the model has to do this balancing act. It has to try and minimize both its original error and this new complexity penalty, all at the same time. So what's actually in this penalty term? Well, it all starts with the model's weights. Just think of weights as the little knobs the model can turn to make its decisions. Big weights mean the model is relying really heavily on certain inputs. So what we do is we take all of these weights, we square them just to make sure they're all positive, and we add them all up. That gives us one single number that kind of represents the model's total complexity. And then we multiply that big number by a value that we choose, called lambda. Lambda is basically our tax rate. It's the dial we can turn to control exactly how much we want to penalize that complexity. Okay, so that's the what, but why? Why does punishing big weights actually stop the model from overfitting? Let's get into the intuition behind all this math. Yeah, this is the big question, right? It seems a little abstract. How does just making a bunch of numbers smaller lead to a simpler model that actually does a better job in the real world? It's a fair question. Okay, so here's how it plays out, step by step. First, we turn up our lambda, our tax rate. Now, the model is forced to start shrinking its weights down towards zero, just to keep its total score, its total loss low. As those weights get smaller, the impact of some of the connections inside the network gets weaker. And what does that do? It makes the overall model conceptually simpler. It forces the model to focus on the big, important patterns in the data, instead of getting distracted by all the noise. And the end result? A simpler model that generalizes way, way better. And now, for what is honestly the best part. After all this theory, you might be thinking, okay, this sounds complicated to actually put into practice. But in modern frameworks like Keras, it's shockingly easy. You see this? This one little line of code is all you need. When you're defining a layer in your neural network, you just add this one argument.
The L2 part tells it to apply that L2 penalty we talked about, and the 0.01, well, that's our lambda. That's our tax rate. That's it. It's that simple.
No, really, that's it. That's the whole thing. One line of code to put this incredibly powerful technique into action. A technique that helps your model generalize, that helps it avoid overfitting, and makes it perform better where it actually counts on new data it's never seen before. It's just an amazing example of how a really complex theory can be made super simple in practice.
So let's recap the key takeaways here. First, overfitting is what happens when a model just memorizes the training data instead of actually learning from it. Second, regularization is our weapon against overfitting. It fights back by penalizing complexity. We talked about L2 regularization, which adds that tax on large weights in the loss function. This whole process encourages a simpler model that's just better at generalizing. And maybe the coolest part? It's super easy to add to your model with just one little line of code.
And that brings us to a final, really important thought. We've seen how powerful regularization is, for sure. But it leaves us with a critical question. If a little bit of this tax helps, is more always better? What happens if you crank that lambda value way, way up? Can you actually oversimplify a model? You absolutely can. And finding that perfect balance, well, that's the art and science of tuning your model. And it's something to definitely keep in mind as you go forward.